honor to talk to you today. It's quite humbling to be here with some of the legends in the room right now, and I hope you will enjoy this talk as much as I enjoyed making it and honoring Rotorcraft Aeroacoustics over the years. Now, I did go a little rogue on the title. Everyone else had, from 1974, till now, 50 years, but I feel that it's very important for us to really appreciate the beginnings as well. All right, and I would like to acknowledge my co-author, who's not here today, but it's legendary Doug Boyd. He'll hate that I said that. And he's from NASA Langley. All right, so first I want to start off by naming the different types of noise mechanisms for rotorcraft. We have thickness noise, loading noise, which includes steady and unsteady terms, and also high-speed impulsive noise. So I want you to keep those in mind because we're going to come back to them soon. All right, so first I'm going to do an introduction where we're going to kind of talk about the history of acoustics within AHS and VFS at the forums. Now for history, we're going to start very early from 1747. We're going to go to the advent of aeroacoustics, and then the beginnings of modern rotorcraft aeroacoustics, and then a summary of those rotor source noises. Following that, we'll go into computational contributions, experimental contributions, and then giving you some comments about looking forward. All right, we begin with the VFS AHS forums. Actually, in 1980 was the first time that we've had an acoustic session at the forum. You will see on this plot here on the y-axis we have number of acoustic papers, and on the x-axis we have the year. I've highlighted 1974 because that's the whole theme of this history talk, so I wanted to make sure that you were aware of that. And 1980 I highlighted of where we had the first acoustic session. Now, in 2016, it was the first person that got the 2016 Nikolsky Lecture for something that was totally acoustics related, and that was Professor Fred Schmitz. Now in 2020, a best forum paper was called Development of Validation of Generic Maneuvering Flight Noise Abatement Guidance for Helicopters, and that was actually the first best paper for the entire forum. So it took a while for us to get best paper, but we got there. That's by Stevenson, Watts, Greenwin, and Pashoni. So technical fellers, there's a couple of legends in here. I won't embarrass them, but Fred Schmitz, he's not here. There was Leverton, Brooks, Tung, Farasat, Jean-Guy Rom, I see you out there. He's out there. Boyd, of course, the co-author of this presentation, and then Professor Brentner, as we all know. Now, there were those other various AHS and VFS special conferences that actually included sessions, but I did not highlight that in the chart here. All right, so now we're going to be moving on to the history. I could start off, really, really early where we're banging rocks and making noise, but I didn't. I started out with the classical wave equation in 1747, which is derived by Jean-Baptiste Laurent d'Alembert. So this right here, you got to know what this is if you want to get into rotorcraft acoustics. This is the equation where it all began. Now, in 1878, Struhal actually found that there was a relationship between frequency and the velocity and length of a string and the diameter of the string. I put a violin here because you can imagine during that time what was, something that was of interest to people, the beautiful violin, those kind of instruments. So these are two early acoustic equations that are something that start the foundation for rotorcraft acoustics. All right, so the advent of aeroacoustics. We've got to mention Navier-Stokes. So in 1822, aerodynamics began with Navier-Stokes equation by expressing momentum equilibrium with conservation of mass. Then, in 1952, Lighthall came along with a theory and rearranged the mass and momentum equation to create a wave equation with sources. So, thing about this is that he did not include surfaces, okay? So this is going to be turbulence. Now, This right here is the famous light hill term, and light hill was actually the catalyst to revolutionize aeroacoustics, but for jet noise. All right, so not us yet, but I mean maybe a little bit in there, maybe a little bit in there. All right, so now let's get into where we started the journey of modern rotorcraft aeroacoustics. So in 1936, we have Gutten, who analyzed sound that was produced by two bladed airplane propellers, dipole noise. Okay, I'll come back to that. The dipole, all that. Just wait. Then in 1937, we have Deming, who derived the thickness noise formation, monopole. And then in 1954, we have Garrick and Watkins, who extended Gutten's work, but accounted it for forward flight. Then moving on to 1969, where we had Lawson and Olerhead, who took Gutten's work and applied it to helicopter main rotor noise. Now, there is a plethora of more people that have contributed. I will name a couple down here. We have Udon, Lyon, Lilly, Sherlin, Hughes, and there are many others. Like I said, this is a brief history, okay? I think we would need to have an entire textbook if we really wanted to cover everything. All right, so here we have Professor Fox William and his student David Hawkins. No, they are not sharing a beer together. That is a Helmholtz resonator. And if and if you go on YouTube, this is quite special. They actually have, it's called Generation of Sound, and you can actually see them professing. So I will say someone in this audience right now had Professor Fox Williams as their advisor. Dr. Brentner was able to experience this in real life, but I'm sure it would be in color when he went there, but that's, yeah. Okay, so what Fox Williams and his student Hawkins did was they rearranged the Navier-Stokes equation to an inhomogeneous wave equation for density with two surface terms. Remember, Lighthill did not do surface terms, and a volume source term. Now here is that beautiful equation right there, and if you look closely, oh, Lighthill comes in there a little bit, right? All right, so now let's talk about in the 1960s what was happening. So there was an increased use of helicopters for U.S. military applications and later commercial certification requirements, and this all resulted in us wanting to expand the rotorcraft acoustic research. Now, before I move forward, I'm going to say 1960s, we're in 1974 now, okay? This is where I probably should have started, but, you know, I think it's very good to appreciate that, and everyone wanted to see them drink a beer together, so we'll keep on moving on. Okay, all right, so in 1980, Ferrosat re-derived the Fox-Williams-Hawkins equation using generalized functions and then derived solutions to the Fox-Williams-Hawkins equation using various acoustic analogies along with methods to solve the wave equation using Green's functions. Now, Ferrosat came up with a lot of different analogies. You have F1, G1, G1A, F2B, etc. But the most widely used formula is F1A. Now, F1A uses impermeable subsonic surfaces and neglects the quadrupole term. So no high-speed stuff yet, right? So down here we have the term of thickness noise and then the loading noise term. I told you these terms are going to come back. They're going to come back. All right. Now, they're coming back again. All right. So I want to go through these again. So we have thickness noise, which is a monopole source. And so you can see this one down here. So thickness noise radiates primarily in front of the rotor over here, and also high-speed impulsive noise does too. Now for loading, we have steady and unsteady terms. For the unsteady terms, we have that blade vortex interaction right here, or the BVI, and also broadband noise. And that is a term of a dipole. So that is this form here. So this is how that sound is radiating out from the source. Now moving on to quadrupole, which is the high-speed impulsive noise. And that is the one over here. And I would like to point out that this lovely figure is by Greenwood, or Professor Greenwood now at Penn State. Now I'd like to move on to computational contributions. All right, so in 1986, NASA developed the first widely used rotorcraft prediction code called WOP-WOP using Farasat's formulation 1A. So Farasat and Brentner developed WOP-WOP. Now, in 1986 to the present, there have been various rotorcraft acoustic prediction tools that have been developed. Now, this includes not only WOP-WOP, but also PSU WOP-WOP. We have ANOP2. We have UCD quietly, and there are a plethora of more, many more codes that have been developed, and I do not want to say that lightly. Now, another art to this is how we provide the input to these codes. Now, the input is going to be dependent upon what's available. Some of it might be limited, and how we provided that has evolved. We now can do compact thickness, compact loading, maybe full surface from CFD, etc. So there's a whole art form to that. There's also a whole art form of how we share that data and how we share results with one another. I'd like to comment on a hemisphere. So I know many of you in this audience have seen this hemisphere. That's another way that we can portray to you our results. Another one is spectrograms. So over the years, the way that we present things has also evolved. All right, again with contributional contributions, some empirical models. So in 1933, STOL and Demi looked at spinning rods, so like a spinning rotor blades, and found that there was a relationship between power and the tip speed. Now, in 1989, which we actually still use this model I'm about to talk about, is the Brooks-Pope-Marcolini. If you remember, Brooks was one of those VFS fellows. And they developed a semi-empirical prediction method for self-noise. And now BPM is used in many of those prediction codes. Probably because they provided the Fortran code and it's really easy just to copy and paste it into the, but anyway, yes, so we still use that to this day since 1989. And here are just some figures down here of all the different types of broadband noise components that were identified with that research. Okay, before I move on to experimental efforts, yesterday we saw Dr. Johnson talk. He was able to give us the background of all the efforts that have went into computational efforts to predict rotorcraft performance. And I do not want to put this lightly, that there has been advancements over the years for comprehensive analysis, CFD, CSD coupling, CFD, which are critical inputs to F1A. So that surface motion and surface loading. And many of those efforts have advanced to validate the efforts for that. So I am not going to go through all those, but I really want to make sure that you guys understand that in a tremendous part of advancing aeroacoustics begins with the advancements of that type of effort. Okay, so now we're going to go to experimental contributions. All right, we're going to start in 1976. So Schmitz and Boxwell acquired far-field acoustic measurements from a UH-1H rotor by placing a microphone on the tail of a very quiet aircraft, an OV-1C. So what they were able to find that there was a difference in pulse behavior for various types of rotor noise sources. I'm sure you've seen this a lot. And it's not going to go away with how they're measuring the acoustics. So let me show you what's next. All right, so that success fed into this in-flight rotorcraft acoustics program, or called IRAP. And so a similar method, but this time they placed microphones on the tips of the airplane and the tail fin of a YO3A, another quiet aircraft, and acquired measurements. Now, they did this several times. So if you look at the bottom here, In 1991 through 1992, they acquired measurements from the S-76C. Then in 1993 from the BO-105, and then moving on to the UH-60A from 1993 to 1994. And then finally they said, oh, let's do some tilt rotor stuff. So we have the XV-15 in 1995. Okay, so continuing on, in 2015, NASA and the Army performed a flight test for various helicopters to investigate the effect of altitude on acoustics. So they tested it over on the West Coast, one at Salton Sea at 0 feet, then at Amadine at 4,000 feet, and at Sweetwater at 7,000 feet. So 3 different test sites. Now, in 2016 to 2019, a large effort by NASA, the FAA, and the U.S. Army conducted the maneuver acoustics test, first for 6 helicopters, and then later they did it for 4 helicopters. I just put a couple of the ones out here, but there was a total of 10 during that time. And they characterized the source for maneuver and approach. Okay, so now moving on to experimental contributions. To begin, I'd like to highlight some of the wind tunnels. Like I said, this is maybe not going to be all of them, but these are the ones that are quite notable within this talk. And this does not include hover chambers, but clearly just wind tunnels. We're going to start out with the National Full-Scale Aerodynamics Complex, the 40 by 8 foot and the 80 by 120 foot wind tunnel at NASA Ames, so just down the road here. So that's at the top here, which is one of the world's largest wind tunnel, excuse me, yes. Then we're going to move across the pond to the German-Dutch wind tunnel, the DNW. And then moving on to a tunnel at Langley, the low-speed aeroacoustic wind tunnel, or the LSOT. All right, so from 1989 until 2009, the NASA Army had the UH-60 airloads program. So in 1989, they first conducted a model-scale rotor test in the DNW wind tunnel. Then there was a full-scale flight test from 1993 to 1994. And then after that, they took that same rotor and put it in the NFACT 40 by 8 foot wind tunnel in 2009. So going from model scale flight tests to wind tunnel test. Now, this led to a long effort of workshops. Data was used for analysis, with the experimental data, predictions, computational improvements. So a lot of effort went into utilizing all the data that was acquired there to help improve and further our understanding. Now we're going to move on to 1994 and 2001. We heard yesterday from Dr. Johnson about the Heart 1 and Heart 2. This was also a very important test for acoustics. It was the higher harmonic control acoustic rotor test in the DNW, and it was an international program with a lot of different contributions from folks. So the objective of this test was to understand BVI noise generation and reduction using higher harmonic blade pitch control of a scaled BO-15 rotor. Now, for this test, they took extensive acoustic measurements, of course, and also the wake flow field measurements. And again, this led to a decade of workshops. So all that effort was not lost, and it was, again, all that data led to further improving our codes and learning more. All right. So now we're going to move to tilt rotors. So in 1997, the XV-15 rotor was tested in the 80 by 120 wind foot tunnel. And they acquired baseline BVI noise and performance measurements for typical descending flight conditions. Then in 1998, we have TRAM, which stands for the Tilt Rotor Aeroacoustic Model Test. Now this was in the DNW, and it was a 1/4 scale tilt rotor in hover, helicopter flight, and low-speed axial flight. And for this test, performance, air loads, structural loads, and also, of course, acoustics was acquired. Now, Moving on to 2009, I know Rom is going to enjoy this one. We have the Boeing Smart Rotor that was in the 40 by 80 foot wind tunnel, which implemented piezoelectric flaps in the blade on an MD-900 Explorer rotor. Now, one thing that came from this test was there was a reduction in thickness noise, so that noise that's radiated in plane of the rotor, that monopole source term, was reduced by 50%, based on directivity, of course, at a microphone. Then, from 2015 to 2018, various testing of small unmanned aerial vehicles, UAVs, less than 55 pounds, was tested in the LSOT at NASA Langley. All right, now going on to urban air mobility. All right, so in 2022, we had the Moog SureFly hover test at the Cincinnati Municipal Airport. Moving on to the Joby flight test in 2022, which was a all-electrical vertical takeoff and landing prototype flight test. And most recently, in 2023, a single Joby rotor full-scale propeller was tested in the NFAC 40 by 80 foot wind tunnel. You may or may not have seen this on the cover of Vertiflight. Here, I was going to say Vogue, but it's definitely Vertiflight. It should be Vogue. Anyway, and yes, so urban air mobility is, those efforts are continuing, and I know we're going to continue to see that in the future as we move forward. Now, looking forward. So for experimental needs, we need more comprehensive data. We need high quality blade motion, blade loading, and more wake measurements. We need to test more articles of multi-rotors, fleets, to understand the noise mechanisms from that. Also, improvements to our measurement hardware. Now, this doesn't only include microphones, microphone stands, or DACs, but also tunnel improvements. As we begin to design rotors that become quiet and quiet and quiet, that background noise needs to also come down so we can get a good signal to noise ratio, so we can really see how loud that rotorcraft is. So improvements to tunnels is very critical if we want to continue to progress forward. Now for computation, I know Wayne says we're only at 10%, and we need to get to 1%, but in order to do that, we need more robust and reliable predictions of rotorcraft acoustics. We need to take advantage of the future high computing capabilities. I know Wayne mentioned maybe possible GUIs, so there's a lots of improvement that can still needs to happen for us to continue to progress looking forward. And I would like to thank the VFS Acoustics Committee and the NASA Ames Aeromechanics Office and interns.